Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to our Organic Chemistry 1 class. Today you will continue on Chapter 10, Alcohols. Reactions of alcohols, substitution and elimination. We have covered these topics before in lecture 28 in alkyl halides. So if we react alcohol with HX, hydrogen halide, like HBr, HCl, HI, we will get the corresponding alkyl halide. This is a primary alcohol, this carbon connecting only to one carbon, so this is primary alkyl halide, and the reaction goes SN2 mechanism. The first step is proton transfer. To form the oxonium ion, which is a good leaving group. So Br minus attack as a nucleophile, kicking the water molecule out, stable leaving group, good leaving group. So nucleophilic attack to give the alkyl bromide. This reaction works well with HBr, but does not work well with HCl. It works, but it does not work well. To replace the hydroxyl group with chloride, we use zinc chloride as a catalyst. What will happen? Lewis acid-base complex in the first step between the alcohol and zinc chloride to form a good leaving group. Then the chloride will attack as a nucleophile and kick this group out. We call a mixture of solution of anhydrous zinc chloride in concentrated hydrochloric acid Lucas reagent. This solution is used to classify alcohols of low molecular weight. The reaction is a substitution in which the chloride replaces a hydroxyl group. A positive test is indicated by change from clear and colorless to turbid, signaling information of chloroalkane. The alcohol is miscible with water, low molecular weight, so it's clear solution. Okay, alkyl halide is different. It's not miscible, so it gives turbidity. Okay, because the difference in polarity, of course. Okay, alcohols with low molecular weight, miscible or soluble in water, while the corresponding alkyl halide is not. Also, the best result for these tests are observed for tertiary alcohol, so tertiary alcohol work fast, and they form respective alkyl halide fastest due to higher stability of the intermediate tertiary carbocation that form very fast. So for tertiary, this is tertiary connected to 1, 2, 3, so that's tertiary alcohol with zinc chloride form acid-base complex. This is very good leaving group. And tertiary carbocation, stable, chloride attack to form the tertiary butyl chloride. To continue substituted and elimination reaction, converting the alcohol to tosylate or mesylate, followed by nucleophilic attack. As we know by now, OH is bad leaving group. In the previous reactions, we activate that OH by protonation to form a better leaving group, water, or we reacted with zinc chloride to form Lewis acid-base complex and form a better leaving group. Here we transfer the OH to tosyl group or mesyl group using tosyl chloride and pyridine. The hydroxyl group is converted into tosylate group, an excellent leaving group. We talked about it before and why. The configuration of the chirality center is not inverted during the formation of tosylate. So because the reaction actually occurs on the OH, not on the chiral center. But it is inverted during the SN2 when you react the tosylate with nucleophile. The net result is inversion of configuration. Starting with this molecule, we have here chiral center. We react this alcohol, secondary alcohol, with paratoluene sulfonine chloride. We call it tosyl chloride, and we give it abbreviation TSCl. In pyridine, and we get abbreviation BY to form the corresponding tosylate. Then the nucleophile will attack SN2 reaction from the backside to kick the tosylate group out via SN2 mechanism to form the corresponding compound. The mesyl chloride is a mesyl group and works well. Okay, too. Yeah. It is methane sulfonyl chloride. So in the tosylation, the lone pair of oxygen will attack on sulfur. We can say that chlorine is getting out. Or to clarify it in more detail, we say, okay, it's attacking on the sulfur, breaking the double bond to form a single bond, which goes back to form a double bond and kick the Cl out. Okay? Then we form this species. Pyridine, which we add in the medium, act as a base and gets this hydrogen out. Then the nucleophile, whatever we have, will attack on the chiral carbon, this carbon, which carries a good leaving group, and the tosylate will go out. Here the pyridine abstract the HCl liberated during the reaction, make the reaction goes forward. All right. Predict the major products of the following reactions. Ethyl tosylate with potassium tertiary butoxide. Here is 2 carbon, and here is tosylate. That's the compound, ethyl tosylate with potassium tertiary butoxide, which is known as a base, as a nucleophile with a primary. So with a primary carbon carrying good leaving group, it will go at low temperature SN2 to form ether, tertiary butyl ethyl ether, or act as a base, the blue line here, to abstract hydrogen and form alkene double bond, and here is leaving group, tosylate, to form ethene. Reaction of isobutyl tosylate with sodium iodide. Here the iodide is nucleophile more than a base, so it will attack via SN2, attack on this carbon, kicking the tosylate out to form 1-iodo-2-methylpropane. Again, reacting hexane 2-yl tosylate with sodium cyanide. Once again, cyanide works as a nucleophile better than base, so it will attack on the carbon, nucleophilic attack, kicking the leaving group tosylate out to form, with inversion, the S2-methylhexane nitrile. So if you started with R, you get inversion, you get S. Remember, it's SN2 mechanism. Cyclohexyl methyl tosylate with ammonia will react again here as a nucleophile, kicking this out, forming the salt, and then excess ammonia will make our compound free amine and form the salt, forming free amine. Okay, so this will act as a base, taking the hydrogen from here to form NH4 plus OTS minus. Okay, N-butyl tosylate again act as a nucleophile, leaving group out to form hex 1N. Reaction of primary and secondary alcohols react with cyanyl chloride or phosphorus bromide via an SN2 mechanism. We have already covered that before, but let's say it one more time. Here, the lone pair will attack on sulfur. As we mentioned, we can say, okay, kick this out, or we can say it's here, then this goes to form negative charge, then comes back, and then this goes out. Anyway, we form this oxonium plus Cl minus deprotonation to form alkyl chlorosulfite. The next step in the reaction may occur by either of two mechanisms depending on the reaction condition. If you use a base such as pyridine in the reaction to neutralize the HCl generated in the steps, leading to alkyl chlorosulfite, an SN2 reaction occur with inversion in configuration, so the Cl minus will attack from the backside of this leaving group, which break down to SO2 and Cl minus. In dioxane as a solvent, the substitution reaction occurs with retention of configuration. The alkyl chlorosulfite undergoes heterolytic cleavage of its CO bond to give a pair of oppositely charged ions. These ions, a carbocation and chlorosulfite anion, remain together as ion pair. Dioxane solvates the carbocation on the side opposite the chlorosulfite. The ion pair reacts with by transfer of chloride ion the same face of the carbocation. So this chlorosulfite sulfide, alkyl chlorosulfide, will dissociate to form ion pair, solvated ion pair. Okay, and these stick together. The dioxane block the backside of the carbocation, so the Cl has to come from the same side to give the chloroalkane with retention in configuration. So the ion pair reacts with by transfer of chloride ion to the same face of carbocation as the original CO bond. This process is called internal return, and the mechanism called SNI mechanism. I refer to internal. So the alkyl chlorosulfide dissociate to ion pair. Dioxane block the backside of the carbocation, led to the attack of the chloride from the same side, and alkyl halide with retention in configuration. Reaction with phosphorus halide again is very similar. The lone pair of the O attack on phosphorus, kicking the Br out, forming this oxonium, good leaving group. Br attacks from the backside, SN2 mechanism, leaving group out. So we started here with S-butanol. We get, because of the inversion, R2-bromobutane. Elimination, E1 and E2 reaction with alcohol, reacting 2-methyl-propane 2-ol with sulfuric acid led to elimination of water to form alkene, isobutene. The first step is protonation. Second step, in this case, because of tertiary carbon leaving group to form tertiary carbocation. Here water acts as base, abstracting H, leaving these two electrons to form double bond. Okay, that's 2-methyl-prop-1-ene. Again, we can achieve the same reaction, 2-methyl-propane 2-ol to isobutene via first tosylation to get a good leaving group, then react this alkyl tosylate with base like sodium ethoxide to get the ene. So that is the first step, tosylation to form the alkyl tosylate, base, take the hydrogen out, form a double bond, get the tosylate anion out. It's E2 mechanism, 2-methyl-prop-1-ene, or what we call it by common name, isobutene. How to make a reduction of alcohols? ROH to RH. We have different methods. We can take the alcohol, convert it to alkene. We have now two methods to do that. Okay, so we can take the alcohol to alkene catalytic reduction using hydrogen and catalyst like platinum. Here we have the product, isobutane. Or we can take the alcohol to tosylate, then react that with lithium aluminum hydride, source of H-. So H- will attack to get this out. Okay, that's roughly, it's not actually H minus, but we can just say the source of hydride. So we kick this out and for the alkane. All right. Recent development. Direct reduction of alcohols can be done using chlorodiphenylsilane as a hydride source in the presence of catalytic amount of indium trichloride. Benzylic alcohol, secondary alcohols, and tertiary alcohols were effectively reduced to give the corresponding alkanes in high yield. A compound bearing both primary and secondary hydroxyl groups was reduced only at the secondary site to afford the primary alcohol after work up with tributyl tetrabutyl ammonium fluoride. This system showed high chemoselectivity only for the hydroxyl group while not reducing other function groups that are readily reduced by standard reducing system. Thus alcohols bearing esters, chloro, bromo, nitro groups, which are sensitive to lithium aluminum hydride or zinc HCl, were selectively reduced only at the hydroxyl site by the chlorodiphenylsilane indium trichloride system. If you would like to read more, go and read Journal Organic Chemistry 2001, volume 66, page 7741. About the mechanism, it's very close to the trimethylsilyl chloride. Here it's attacking on the Si, kicking Cl out, forming this intermediate, which upon adding 5% indium chloride, indium trichloride, we call it oxophilicity, has oxophilicity. Okay, it's oxygen lover, so it makes a complex, oxonium complex. It's acid base, Lewis acid base complex. Okay, which then allow the hydride to attack on the carbon, leaving oxygen, the leaving group out, to form the alkane and siloxane polymer as a byproduct. Oxidation of alcohols. Primary alcohols can be oxidized to aldehyde, which can further oxidize to carboxylic acid. Secondary alcohol can be oxidized to ketone with no further oxidation. Tertiary alcohol cannot be oxidized. If it oxidized, it will be oxidative cleavage with breaking carbon-carbon bond. So that's tertiary alcohol. The most common oxidizing reagent is chromic acid, H2CrO4, which can be formed either from chromic trioxide or from potassium or sodium dichromate in aqueous acidic solution, chromium trioxide or potassium dichromate with sulfuric acid form chromic acid. A solution of chromium trioxide in aqueous sulfuric acid and acetone called Jones reagent. Let's look at the mechanism The alcohol first, and we have here a model primary alcohol. The alcohol and the chromic acid, chrom 6, dehydrate to form ester, elimination of water, to form chromate ester, which then attacked by water molecule as a base to get one hydrogen out, forming double bond, and kick this group out as a leaving group, forming aldehyde. Under this acidic condition, the oxygen protonate, proton transfer from acidified water molecule, then attacked as a nucleophile, nucleophilic attack by another molecule of water to form hydrate, two OHs on the same carbon. Again, chromic acid form ester with one of these OHs. Molecule of water will act as a base, proton transfer, forming double bond, kicking this out to eject chromous acid where chrome is 4, and the rest will be the carboxylic acid. So primary alcohol, first oxidation to an aldehyde, second oxidation will be carboxylic acid. Pyridinium chlorochromate, BCC, is a milder version of chromic acid. It oxidizes primary alcohol to aldehydes with no further oxidation. Of course, it oxidizes secondary alcohol to ketone. Similarly, Collin reagent, which it is chromium trioxide in pyridine, that's Collin reagent. It's complex between the nitrogen of pyridine and the chromium in chromium trioxide, whereas pyridinium chlorochromate is chromium trioxide, HCl and pyridine, to form this salt. So primary alcohol with BCC form an aldehyde and stop. No further oxidation. Again, the lone pair of OH attacks on the Cr, chrome, with cleaving this carbon double bond to single bond, so it will have the O minus. Then proton transfer from here to one of these oxygen. Then back this lone negative charge to form a double bond with Cl out. Then the Cl will attack one of these hydrogens of the primary alcohol, forming a double bond, and this group is out, form the aldehyde, chromous acid, and pyridinium chloride. Oxidations using sodium hypochlorite can accomplish the same oxidations as chromic acid without using heavy metals and without generating hazardous waste. Primary alcohol react with a mixture of sodium hypochlorite in HOCl, first protonation, proton transfer, then the hypochlorite attack as a nucleophile, kicking the water molecule out. Water will react as a base, abstracting this hydrogen These two electrons form a double bond and Cl out to form the aldehyde. The aldehyde under this acidic condition protonates. Hypochlorite will attack as a nucleophile, add to this double bond, forming this species. Water as a base again, since we have carbon hydrogen, abstract this hydrogen, forming double bond, kicking this out, forming the carboxylic acid. Looking forward to seeing you in class. Bye bye.